Hi everyone, this is the second part of graphical summaries. Outcomes, of course, know the definitions, the purpose of graphical summaries, which graphical method is best suited for your data that you have. I'll refer you to the lesson on the different types of data. Then here, you must be able to know how to construct histograms, polygons, and ogives, which are the three charts, or graphs rather, we'll be looking at. And the reason that you must be able to construct them is because software packages do not give you exactly what you want, and you must be able to modify the graphs slightly so that it actually represents the data properly. Also, when we get to histograms, then you'll see that there are software packages like Excel that requires you to provide the software with information that you can only obtain by first doing some other calculation. Right, and then of course the most important is extracting information from the graphs regarding the data that it summarizes. Right, now previously we looked at a dot plot, and this was the example that we considered, and we saw the advantages and disadvantages. Mainly it's used to detect patterns in datasets, but it's only really suitable for small samples and small ranges. So small range like from 0 to 4. If we extend this and we construct a bar graph on top of this, where we have a bar for each one of the different outcomes, 0 to 4, and the height of the bar represents the number of households. So in other words, the number of observations in here. So we just count how many dots we have, and that will be the height of the bar. Then this is what we call a discrete histogram, right? A discrete histogram. Now, the difference between a bar chart and a histogram is for our discrete histogram, every bar has a width of 1 unit, and there are no gaps between the bars because the x-axis represents the number line. So there should be no gaps over here. Whereas a bar chart, we have categories. In other words, there might not be a natural order to what you are representing on the x-axis, so the order doesn't always matter. And because it's categories, we usually leave gaps between to show that these things are separated from each other. Right, however, the uses is still the same as for a dot plot when we talk about our discrete histogram. But this is the type of thing that you will see when you look at articles regarding data analyses and research findings. You will see these types of histograms. Now, instead of having the raw data, okay, remember this is the raw data, it hasn't been processed, it's just written down as it was recorded. As opposed to the raw data, we can have group data. So here we have the the 5 different outcomes, families with no vehicles, up to families with 4 vehicles, and the frequency for those families. So there's one family with no vehicle, 4 with 1, 9 with 2 vehicles, 5 with 3 vehicles, and 1 with 4 vehicles. And the number of households will be on the y-axis, and we'll call that the frequency. Now we can change that to the relative frequency. Now relative frequency is exactly what the name says. It is a frequency relative to something else. In this case, relative to the sample size. We have 20 observations, so the relative frequency for the first class will be 1 over 20, which is 0.05. For the next class, the relative frequency will be the frequency relative to the sample size, so that's 4 over 20, which is 0.2. Doing that for each one, we will end up with the last one, 0.05. Now what you should notice is that the change between the two histograms, where this one was the frequency and this one is the relative frequency, the actual shape and size of the histogram did not change. The only thing that changed was the y-axis labels. That's because the ratios remain the same. This is still 1 out of 20, where the total now is 20. This is just the fraction version of that. If we extend it to percentage, then we just take the relative frequency and we multiply it by 100. So you'll see again, the graph did not change. It's only the y-axis labels that changed. Right, because the scale is basically still the same. Size and everything remains the same. Then lastly, we have the cumulative values. So here we have the cumulative frequencies. You'll see it's also pink, like in that case, so that you can associate it with the frequency. The cumulative relative frequencies and the cumulative percentages. So this simply means that we're adding up as we go along. In the first class, we only have one family. In the second class, we have 4 families, but the cumulative will be 1 plus 4, so that gives us 5. Then the next one will be 9 plus 4 plus 1, so that gives us 14. The same for the cumulative relative frequencies. We will add up the relative frequencies as we go along, and the same for the percentages. So for the frequencies, we have to end with the sample size of 20, because by the time we get to the end of the table, we've added together all the frequencies. The relative frequencies will sum to 1, and the cumulative percentages will end up being 100, which is just 100% of the data. Now, if we look at the actual bars, and I made a note here, important for later, we usually refer to the area of the bar as a percentage. And that becomes very important at a later stage for the rest of the course, because every time we talk about area, we'll talk about either percentage or probability. So if I take this bar, for example, then the area of this bar will represent 45%. Now, how can I say that? Well, if we look at just basic geometry, the width of the bar is 1 unit, because it goes from 1.5 to 2.5. The height of the bar, this is percentage, so the height of the bar for 2, so there we have 2, the height of the bar is 45, so if the height is 45 and the width is equal to 1, then 1 times 45 is 45%. Right, so the area of the bars. So this bar here, for example, will also have a width of 1 unit, because it goes from 1/2 to 1.5. The height of this one will be 20%, so the height times the width will give us 20% area of the bar. Right, so just in conclusion, when we compare the frequency, relative frequency and percentage, then it's just the y-axis labels that change. The actual discrete histogram itself, the shape, the size, nothing else changes. Right, now next we look at continuous data. Now remember, continuous data is data with decimals. Now let's take a look at an example. Here I have the weight in kilograms of 55 bags of cement. You can see that it's not very nice measurement, 73.3, and the last one here is 70.8. If I were to start off like I did with the other example and construct a dot plot first, then what we'll see is that the dot plot is very cluttered. We'll start off with the minimum value 64.4, maximum value is 75.9, and of course everything else will be in between. There's a lot of overlapping over here because we have these decimal values, so the dots will be in the decimal positions, causing this overlap, and it's just way too cluttered. We can see here that there's a concentration of values, measurements over here, and there's fewer to the sides, but we don't really have a very good idea of how it looks. So what we do is we will create classes. In other words, we will create groups, and then we will combine the values in groups. So I might have groups looking like that, and then I will count the values or the number of values in each of those groups, and I will simply construct bars to the height. So here my y-axis might be the frequency, and I'll just count how many values are in that group, and I'll make a note here, count how many in that group, make a note, and the same for the rest, until I've covered all the observations in my dot plot. So now let's have a look at the process which we need to follow in order to do this. First thing is the starting point of the classes. Where do we start? Now the usual is to take the minimum value in the data set and then subtract half a unit. So if we look at our data set over here, then the units is 0.1. So that means we will take 64.4 and we will subtract half of 0.1. So 0.1 times a half, that gives us 0.05. So we get 64.35. So that means our very first group boundary, lower boundary, will be 64.35, and we do that to ensure that the smallest value in the data set is included in the very first class. So 64.4 is a little bit bigger, so it's going to fall inside. Right, then the next question, how many classes? Now there's a few different ways in which we can determine the number of classes, but the most common one that you'll see in many books is called Sturge's rule. Sturge's rule says a number of classes can be determined by taking 1 plus 3.3 times log of the sample size, and we round that to the nearest integer. So for our example, we have n equal to 55. So we will put 55 into n, take log of 55, that answer times 3.3, that answer we'll add 1 to it, and that gives us this 6.74. Rounding that gives us 7. So that means we will have 7 classes. Starting over here with 64.35, we will have 7 classes going up. Now please take note, there should be no gaps between the classes because these are decimal values and they can slip through the gap. These classes need to be adjacent, no gaps, so that everything, all the observations have a place to be grouped into. Right, so Sturge's rule tells us a number of classes, we round that to the nearest integer, and the number of classes is usually denoted by a lowercase k. Right, now the next thing, the size of each class. How big must these classes be? It's pointless to have a class starting here and we have 7 classes and then make the first class to end there and then start the second class there and end it there, because that means the other 5 classes will then be empty because everything is sorted into the first 2. Right, so we need to determine the number of classes so that we just cover the necessary distance on the x-axis. We don't want to go too far beyond because we don't want classes that are empty. Right, so the way in which we determine the number of classes is by taking the range and dividing it by the number of classes. Now, what is the range? The range is simply the difference between the largest value and the smallest value in the data set. So in this case, 75.9 minus 64.4, that gives us 11.5. So now that we have the range, in other words, we know what distance needs to be covered, we divide that by the number of classes, which is 7, and then we know how big each class must be. In other words, we know the width of each class. So what we'll do is we'll calculate the width by taking the range, okay, which is 11.5, dividing it by the number of classes, which is 7. We get 1.64. Now the rule is to round up to the next unit. Now remember, the unit was 0.1. So we need to round up to 1 decimal place, and that will give us this 1.7 over here. So if this is the size of each class, then we'll start with the smallest value, which is the 64.35, and we will add 1.7 to it. And that gives us 66.05, which is our first class. The first class then goes from 64.35 to 66.05. So the next class will start at 66.05 and it will go up by 1.7. And that will take us to 67.75. And then we'll add another 1.7. And we'll keep on adding 1.7s until we have 7 classes, because that's what Sturge's rule gave us. According to this calculation, we should have 7 classes. Now you'll see the last one over here is 76.25. The largest value in the data set is 75.9. So that means that this last class ends slightly above the largest value. This last class starts below the largest value, so it means that we don't have empty classes because the last class does in fact contain a value. Right, so once we've done that, then we have our foundation for our histogram. We have the number of classes, from Sturge's rule, we have the range, and we divide that by the number of classes to give us the class width, which was 1.7, rounded up to the next unit. We keep on adding that until we have 7 classes. Now what you should note, really important, by taking the smallest value in the data set, 64.4, and subtracting half a unit from it, that gave us 64.35. All the boundaries have a 5 at the end, and all the boundaries have 2 decimal places. See, all the boundaries have 2 decimal places, which is what must happen. The boundaries must always have one more decimal place than the data, and it will end in 5 because we're taking half a unit. So that automatically gives us a 5. So I'll repeat that again. All the boundaries must end with a 5 because it's half a unit, and all the boundaries must have one more decimal place than the data. Because if the boundaries have also one decimal place, we could have a value that's equal to a boundary. And where do we put that? If I have a value that's equal to 66.05, does it go in class 1 or does it go in class 2? So we don't want a situation like that. So that is why we go through this process. If we have data which has 2 decimal places, so let's say instead of 67.1 we have 67.12, then our unit will be 0.01, and we will take half of that, so that means we will have 0.005, and we'll subtract that from the smallest value in the data set, and we will also round our class width then not to 1.7 but to another decimal, so that we have 3 decimals in the boundaries because we have 2 decimals in the data. Right, so from that we can construct our histogram, because we simply count now how many observations we have in each class. Remember, these are the class boundaries. So we count how many values in each class, and we construct the height of the bars according to those frequencies. Right, and this we call our histogram. And this is a histogram for continuous data. So it's a little bit more effort to actually construct this, but it is a general chart, or graph rather, that you will see in many articles. Right, now our histogram is suitable for quantitative data. Remember, quantitative, it's measurements, and I said in the beginning, with histograms our x-axis is the number line, so it must be quantitative data. Can be very large data sets, can accommodate many different values, and we use it to detect patterns. So you can see there's really no disadvantages to this, so that's why it's such a common or popular method. We can construct exactly the same type of table as we did before for the discrete data. The only difference now is we will take this interval over here, which is the first class, going from 64.35 to 66.05, and we'll indicate that as the first class on our table. Count how many values are in there. There were 3 dots, so the frequency is 3. We have 55 values in total, so 3 divided by 55 gives us our relative frequency, times that by 100, that gives us our percentage. So we do that for the next one as well. It starts at 66.05, ends at 67.75, there it is. Count how many dots, we see that it's 7, so the frequency is 7. Divide that by 55, which is our sample size, to get our relative frequency, times that by 100, which will give us our percentage. If we add the values as we go along, we get the cumulative values. So 3 plus 7, that gives me this 10, 0.05 plus 0.13, that gives us 0.18, and 5 plus 13, that gives us 18. Right, now there's one more that we have for this histogram as opposed to the previous one, and the extra column will be the midpoint column. Now the midpoint is also called the class mark. Now calculating a midpoint is very easy. We simply add the lower boundary and the upper boundary, and we divide it by 2. So if we do that for each one, These will be the midpoints. Now if we take these midpoints and we indicate them on the histogram. Now remember, first class has a midpoint of 65.2. That's this class over here. The height of this will be the frequency for my graph over here. So the height of 66.9 will be at frequency 7, and I'll continue in that way. Then I will end up with what we call a frequency polygon if I connect all of those points. However, this polygon is floating in the air. We can't have that. So what we'll do is we will pretend that there's another class before this one. So what we'll do is we'll take this lower boundary and we'll subtract 1.7 from it, and that will give us 62.65. The midpoint will be over there. It has 0 frequency, so it's sitting on the x-axis, and over here we'll take our midpoint and we will add 1.7 to it to get this one, and we'll connect. So that will give us our frequency polygon. Right, so these bottom two, or rather the bottom one over here and the top one over here, they don't exist in the data set, so that's why they have a frequency of 0, and we simply include them so that we can anchor our frequency polygon so that it doesn't float in the air. Right, now the frequency polygon is usually rounded. We talk about distribution curves at a later stage, but that is sort of the common notation that we use and the common appearance of a polygon. It's not usually angled, it's usually rounded. Right, now the next type of graph after the histogram and the frequency polygon is what we call the ogive. Now the ogive is a cumulative graph. So if we think of cumulative, then this last 3 columns should come to mind because we are accumulating. So what we'll do is we'll start off by asking the question, how many values do we have accumulated up to 64.35, which is the very first boundary that we have? Now the answer is that we have no values at that stage because the smallest value in the data set is 64.4. Remember, the lower boundary was created by taking the smallest value and subtracting 0.05 from it. So we don't have any values at this stage. So we'll make a dot on the x-axis at 64.35, and the frequency or the height of it will be 0 because there's nothing accumulated. Then the next question, how many values do we have up to 66.05? Well, that's the end of the first class. And at the end of the first class, I've already got 3 values. So I'll make a dot at height 3. Then next, how many values do I have up to 67.75? Well, up to 67.75 means that I've added 3 and 7, which is my cumulative 10. So if I carry on in that way, going all the way down to the last value in my cumulative column, I'll get 55, and that will be the highest point at 55 because there's no more observations. So at this stage I have nothing, so that's 0, and at this stage I have everything, which is a total of 55. If I connect that, then we have our ogive curve. Now the ogive is useful for detecting or estimating percentiles. Now what is a percentile? We'll get into more detail a bit later, but for now we can just identify it as a value that divides the data set into 2 parts. Okay, it divides the data set up into 2 parts. Now also what you'll notice is that whether I have a cumulative frequency on this axis or whether I have cumulative percentage or whether I have cumulative relative frequency, the shape does not matter. It's not affected. It stays the same. It's exactly the same as with the histogram and the polygon. Doesn't matter what I have on here, whether it's percentage, relative frequency, or frequency, the shape of the distribution stays the same. So now if I have cumulative percentage over here, then I can ask a question like, what weight separates the lowest 20% from the rest? Now remember, this is cumulative. This is a number line. We started off with a dot plot. That means all the data was arranged from smallest to largest. And remember, we're working with weights. And the question is, what weight separates the lowest 20% from the rest? Well, here we have 20%. And here we have below 20%. So if we move across, then we'll find the cutoff point on our graph. Moving down, we see that approximately at 67.75 kilograms, we have the cutoff point for the lowest 20%. So that means that 20% of our data set have weights less than or equal to 67.75. Right, now, just to recall and go back to what we had with a discrete histogram, I said that the bar area represents percentage, so the same will be true in this case. However, if we were to do the area calculation, it's not going to give us 35% because of the width over here, but there is an adjustment we can make, but we're not going to bother with all of those calculations. It's the idea that is the most important, and the idea is that we look at the area of the bars to give us an indication of the percentage of the data that fall in that class. So this bar has a height of 35%, so I will just say that 35% of the data is indicated or illustrated by the area of this bar. So 35% of my data lie inside of this interval. Remember, the actual observations are sitting over here on the x-axis. This area just tells me how many observations are sitting on this x-axis. Okay, let me repeat that. The actual observations are sitting on the x-axis. The area tells me how many observations I have there. If I were to revert to my frequency polygon, it'll be exactly the same situation. The area under the curve gives us our percentage of values that fall within a specific group or a specific class. Now, it was mentioned that the advantages of a frequency polygon and histogram is so that we can detect patterns in the data set, and that's one of the main purposes. So if we look at the summary over here, where we have a frequency polygon that looks like this, then we can say that it is symmetric because we're able to divide it up into two equal sides. Okay, the one being a mirror image of the other. So in this case we have symmetry. Now see what I mentioned about the distribution curves. This is a curve that is a rounded polygon. The polygon comes from connecting the midpoints on the histogram. In this case we have a distribution that is skewed to the left. So that means we have very few small values and we have many large values. Remember, number line, so we have small values over here and we have larger values, let's say smaller, so smaller and larger values, and then the height of the bars, but remember the bars, we can't see them here, so we need to look at area under the curve, and if it's a very big area it means many values. So this is many values that are larger, few values that are smaller. And this is the opposite. This is skewed to the right, or positively skewed, because the larger values are over here and the smaller values are now over here as well. There's very few smaller values. If we think of the histogram that's sitting underneath here, very few smaller values, and then as we go slightly up we have many smaller values, but if we look over here we have really big values but very few of them. So if we have something with a tail on the right, we say that it's positively skewed. Tail on the left, we say that it's negatively skewed. And if we have extreme values, like values that's sitting down here that are really, really small, or values that are sitting up here that are really, really big compared to the others, then we say that these extreme values are called outliers. Right, and we'll be looking in a little bit more detail at outliers in the later section. Right, so to end with, we have many different distribution shapes. In other words, the data can be distributed in many different ways. This one is the ideal one because mathematically it has many advantages. Symmetric and bell-shaped. Symmetric because we can split it into two and the one side will be a mirror image of the other. This is symmetric but not bell-shaped. This is skewed to the right, which we just saw, skewed to the left. This one is exponential, right? Decreasing exponentially. This one is bimodal. Now you've probably heard the term mode before. We'll discuss it in the next section. But a mode is just the value that appears the most. So if we look at this, then right in the middle here on the x-axis, we're going to have a value that appears the most. Over here, off center, we're going to have a value that appears the most. Remember, the value itself is on the x-axis. How many times it appears, or its frequency, will be the height of the bar. So here we have two values that appear many times. So we say that our distribution is bimodal. Right, these are just a few basic shapes. We get other more technical, complicated shapes, but for our purposes, we will just be looking at these until you have a little bit more experience with distributions.